There is something timeless about looking up at the night sky. Thousands of years ago, our ancestors gathered around flickering campfires and gazed into the stars, wondering what lay beyond the darkness. Today, despite all our technology and knowledge, we still find ourselves doing the same. We build telescopes, launch spacecraft, and send our machines farther than we ourselves can go, all in pursuit of a single, ageless question: what is out there? The universe above us is not just a canvas of stars. It is a mirror to our own curiosity, a reflection of our desire to understand our place in everything. From the silent beauty of distant galaxies to the eerie glow of dying stars, the cosmos invites us to explore. It offers no easy answers, only mysteries that grow deeper the further we reach. And yet, we keep reaching. We peer into the past through light that has traveled for billions of years. We follow probes as they drift into interstellar space, and we dream of worlds beyond our own. Why? Because in the darkness, we see potential. In the unknown, we find purpose. To look up is not just to seek answers. It is to affirm that we are part of something vast, ancient, and extraordinary. For decades, we have dreamed of a telescope powerful enough to look back in time, to see the first light in the universe, the formation of stars and galaxies, and perhaps even signs of life beyond Earth. That dream now has a name: the James Webb Space Telescope. This remarkable instrument represents the pinnacle of human engineering, science, and imagination. It is more than just a telescope. It is a time machine, a cosmic observatory, and one of the most ambitious space projects humanity has ever undertaken. Designed to observe the universe in infrared light, James Webb opens a new window into the cosmos. While the Hubble Space Telescope revolutionized our view of the visible universe, James Webb allows us to see much further and deeper. Infrared light can penetrate thick clouds of gas and dust that once blocked our view. More importantly, because the universe is expanding, the light from the earliest galaxies has been stretched, redshifted, into the infrared spectrum. To see those ancient structures, we must use an infrared telescope, and there is none more powerful than this. James Webb's mirror spans 6.5 meters across, over 6 times the collecting area of Hubble's mirror. That size gives it unmatched sensitivity to faint light from distant stars and galaxies. But the mirror was too large to fit into any existing rocket. So it had to be folded, like a giant piece of origami, to launch into space. Once in orbit, hundreds of motors, pulleys, and tensioning systems worked in perfect sequence to unfold and align the telescope. A ballet of engineering, executed flawlessly. Keeping the telescope cold was equally vital. Infrared detectors are so sensitive that even the telescope's own warmth could drown out the faint light it is trying to detect. To prevent this, engineers built a sun shield the size of a tennis court. This 5-layered membrane blocks heat and light from the sun, Earth, and Moon, allowing the telescope to cool down to temperatures just a few degrees above absolute zero. It is one of the coldest, most stable environments ever achieved for a space-based observatory. The path to launch was long and fraught with setbacks. Originally envisioned in the 1990s, the telescope was expected to cost around $1 billion and launch in the early 2000s. But as the complexity of the design grew, so did the timeline and the budget. Years turned into decades. The final cost reached $10 billion. Along the way, the project faced more than 300 potential points of failure. Each had to function perfectly, or the telescope might never work at all. But in December of 2021, after years of anticipation, James Webb finally launched. It took nearly a month for the telescope to reach its destination, an orbit around a point called Lagrange 2, roughly 1.5 million kilometers away from Earth. There, it began the delicate process of unfolding, calibrating, and cooling down. Engineers monitored every step, holding their breath. One by one, each subsystem came online. The mirrors aligned, the sun shield deployed, and the instruments powered up. Slowly, James Webb came to life, and with it, a new era of astronomy began. On board, 4 main instruments work together to observe the cosmos: the near-infrared camera, the near-infrared spectrograph, the fine guidance sensor, and the mid-infrared instrument, known as MIRI. Together, they can detect the faintest glimmers of ancient starlight, analyze the atmospheres of exoplanets, and pierce the veil of dust around newborn stars. The level of precision is astonishing. James Webb can detect the heat signature of a bumblebee on the moon. It can see further into space and further back in time than anything that came before it. But this telescope is not meant to replace Hubble. It is meant to complement it. While Hubble specializes in the ultraviolet and visible light spectrum, James Webb focuses almost entirely on infrared. Each reveals a different layer of the universe, and together, they offer a more complete picture than either could alone. We now stand at the edge of a new horizon. With this extraordinary tool, we are not just gazing into the cosmos, we are witnessing the birth of stars, the glow of ancient galaxies, and perhaps one day, the unmistakable signs of life elsewhere in the universe. When the first images from the James Webb Space Telescope were unveiled, the world paused. Scientists, children, artists, and dreamers alike stared into the void and saw wonder, detail, and depth unlike anything ever captured before. These were not just photographs. They were fragments of time, fossilized light traveling for billions of years, reaching our tiny world at last. The images were crisp, vibrant, and layered with structure, full of turbulence and order, chaos and beauty. They showed us that the universe is alive with motion, complexity, and scale beyond human imagination. Among the first images was the breathtaking portrait of the cosmic cliffs, a towering landscape within the Carina Nebula. What appears like a jagged mountain range is, in truth, a region of intense star formation. The glowing peaks are massive clouds of gas and dust, rising over 7 light-years tall. James Webb's infrared eyes revealed infant stars hidden within the mist, stars that had never been seen before. These were not static sculptures. They were dynamic factories of creation, forging elements, stirring shockwaves, and shaping entire solar systems from molecular clouds. Next came a view of the Southern Ring Nebula, the final breath of a dying star. What looks like a delicate bubble of light is actually the remains of a sun-like star shedding its outer layers into space. Inside its core lies a white dwarf, the final ember of a once vibrant furnace. Using its dual instruments, James Webb captured 2 views, one in near-infrared, revealing layers of gas and dust flowing outward, and one in mid-infrared, exposing the central star in stunning clarity. Death, it turns out, is not an end in the cosmos. It is the beginning of something new. Another astonishing image came from the Tarantula Nebula, a region in the Large Magellanic Cloud where stars are being born at a furious pace. It is a stellar nursery unlike any in our Milky Way, a chaotic web of gas and radiation sculpted by powerful stellar winds. With Webb's instruments, astronomers observed hundreds of never-before-seen young stars, blazing with ultraviolet light and carving out vast cavities in the surrounding nebula. This region offers a rare glimpse into what the universe looked like during its most productive period of star formation, some 10 billion years ago. Then came the Stephan's Quintet, a galactic dance frozen in motion. This group of 5 galaxies, bound by gravity, is engaged in a slow collision that will unfold over millions of years. James Webb revealed swirling tails of stars, shock fronts of intergalactic gas, and glowing regions of active star formation where galaxies crash together. The image is vast, so large that it was composed of nearly 1,000 separate exposures stitched into a single mosaic. It is not merely a snapshot. It is a cosmic symphony of gravity and time, playing out on a scale we can barely comprehend. Perhaps the most iconic of all the early images was the first deep field, a region of sky no larger than a grain of sand held at arm's length. And yet, within that minuscule area lies thousands of galaxies, each containing billions of stars. Some of the galaxies are stretched and distorted, magnified by gravitational lensing caused by massive galaxy clusters in the foreground. Among them, astronomers found some of the most distant galaxies ever observed, their light traveling for more than 13 billion years before reaching James Webb's golden mirror. In this single frame, we peer into the ancient past of the universe. What makes these images extraordinary is not just their beauty, it is what they tell us. Each photon of light collected by Webb carries information: temperature, chemical composition, movement, and age. By analyzing this data, astronomers can reconstruct the birth of stars, map the evolution of galaxies, and search for signs of life in the atmospheres of exoplanets. These images are more than art. They are data-rich windows into the laws of physics, revealing how gravity sculpts matter, how energy flows, and how complexity arises from simplicity across cosmic time. With just its first few images, James Webb has already reshaped how we see the universe. It has shown us that the cosmos is not distant. It is unfolding, breathing, and alive in ways we are only beginning to grasp. From stars being born in turbulent clouds to galaxies colliding in slow-motion ballets, the telescope invites us not just to observe, but to wonder. We are witnessing the universe in its youth, in its struggle, and in its grandeur. And this is only the beginning. The first images are a promise, one that says the greatest discoveries still lie ahead. To observe a galaxy is to peer into a structure far grander than ourselves, an island of hundreds of billions of stars, suspended in a sea of darkness. Yet many of the galaxies we now observe lie so far away that their light began its journey when the universe was still in its infancy. The James Webb Space Telescope allows us to see these distant giants not as they are now, but as they once were, mere flickers in a cosmic dawn. With its infrared vision, Webb reaches across space and time to reveal how galaxies formed, grew, collided, and evolved. Among the most captivating targets is Stephan's Quintet, a compact group of 5 galaxies locked in an intricate gravitational embrace. 4 of them lie about 300 million light-years from Earth, weaving through each other in a slow, elaborate dance that will eventually reshape them into a single structure. James Webb captured this scene in stunning detail, revealing glowing shockwaves, tidal tails of stars, and enormous clouds of gas set ablaze by collisions. This is more than a beautiful image. It is a window into galactic evolution, into the way galaxies merge, consume, and create. The complexity in Stephan's Quintet is only the beginning. James Webb's deep field observations have unveiled galaxies we never knew existed, tiny, red-shifted smudges at the very edge of visibility. These ancient galaxies appear smaller and denser than those in the present-day universe, yet they are bursting with activity. Some are forming stars at rates far higher than expected. Others challenge our models of cosmic structure. They force us to rethink when and how galaxies first appeared, and whether we truly understand the forces that shaped them in those first few 100 million years. One of the key tools that makes this possible is gravitational lensing. When light from a distant galaxy passes through a massive cluster of matter, gravity bends and magnifies that light like a lens. James Webb uses this cosmic trick to study galaxies that would otherwise be too faint to detect. In doing so, it allows us to observe the universe as it was over 13 billion years ago. These lensed galaxies do not just offer incredible views, they offer insights into the earliest stages of galaxy formation and into the distribution of dark matter in the universe. Some of the galaxies discovered by Webb appear surprisingly mature for their age. Their structures suggest that they formed stars and built complexity far earlier than we believed possible. These findings have sent shockwaves through the field of cosmology. They raise new questions. Did the first galaxies form faster than our models predict? Are we missing key ingredients in our understanding of the early universe? Or is there something more exotic at work, perhaps physics beyond the standard model, echoing from a time before the first atoms existed? What James Webb offers us is not certainty, it is vision. It shows us that the universe is deeper, richer, and stranger than we thought. Distant galaxies are not relics of the past. They are living records of cosmic history, each one a chapter in the great story of how the cosmos came to be. As we continue to gather light from these faraway beacons, we are not just learning about galaxies. We are learning about ourselves, our origins, our destiny, and the quiet, enduring light that connects all things across time and space. Before James Webb opened the veil of the infrared universe, there was another eye in the sky, one that changed everything. Launched in the spring of 1990, the Hubble Space Telescope became one of humanity's most celebrated scientific instruments. Floating above Earth's atmosphere, it offered us our first clear view of the cosmos, unblurred by clouds or turbulence. Over the decades, Hubble has shown us galaxies colliding, stars exploding, and clusters dancing through space like ancient constellations made real. It gave us clarity where there had been haze, and with it, perspective. Among Hubble's most haunting portraits is the Butterfly Nebula, an immense cloud of gas cast off by a dying star. With its elegant wings and glowing filaments, the nebula stretches for more than 3 light-years across, a final gesture of stellar beauty before silence. Hubble captured this farewell in vivid color, revealing patterns shaped by magnetic fields and stellar winds. Such images are not only aesthetically captivating, they allow scientists to study how elements are recycled into space, becoming the building blocks for new stars, planets, and perhaps life itself. Hubble also revealed the secrets of massive stars, like those in the Pismis 24 cluster. For years, a star within this cluster was thought to be the most massive ever discovered, estimated at over 200 solar masses. But Hubble's keen resolution revealed the truth. What appeared as one colossal star was actually 3 distinct stars tightly packed together. This discovery reshaped how we measure stellar mass and reminded us that resolution, both literal and metaphorical, can change our understanding in profound ways. Not all of Hubble's discoveries focused on what is present. Some revealed what was once there and what remains behind. The Palomar 12 globular cluster, once thought to belong to the Milky Way, was found to carry a different signature, a different motion, a different past. Evidence suggested it came from the Sagittarius dwarf galaxy, which was torn apart by our own galaxy's gravity long ago. Palomar 12 is a relic, a fossil from a celestial collision. It stands as a quiet testament to the violence and hunger of galaxies in their quest to grow. With every image, Hubble deepened our sense of scale. From sweeping views of spiral arms to tight shots of nebular cores, it painted a universe that was not static, but alive, growing, changing, and evolving. It observed supernovae exploding in far-off galaxies and measured their light to help determine the expansion rate of the universe. In doing so, Hubble helped reveal the presence of something unseen: dark energy, a force causing the cosmos to stretch faster over time. These were not just photos. They were measurements of reality itself bending under unknown laws. For over 3 decades, Hubble has been our silent companion in orbit, watching, recording, and reminding us that the sky above is not empty. It has shaped our imagination, our science, and our place in the cosmic story. And though James Webb now peers further into the past, it stands on the foundation that Hubble built. Together, these telescopes do not compete, they harmonize. One sees the ancient glow through dust and time, the other captures the brilliant structure of stars and galaxies in visible light. Side by side, they reveal the universe in full. Galaxies are not mere collections of stars. They are gravitational cities, built from luminous matter, dark matter, and time. Each galaxy spins, breathes, and evolves across billions of years, shaped by forces we still struggle to understand. Some, like the Sombrero Galaxy, dazzle with symmetry, a luminous disk encircled by a dark, shadowed halo of dust. With its bulging central core and smooth spiral arms, it appears almost architectural, as if the universe itself had sketched it with intent. Yet even such beauty is a disguise, concealing the invisible scaffolding that holds it all together. That scaffolding is dark matter, a substance that neither emits nor reflects light, and yet exerts an enormous gravitational pull. It is the silent architect of the cosmos, influencing the shape and motion of galaxies. We know it is there not because we see it, but because we see what it does. Galaxies spin faster than their visible mass should allow. Clusters of galaxies remain bound despite their enormous velocities. Something unseen is holding them together. Something that makes up the vast majority of all matter in the universe, yet remains beyond our touch. One of the first clues came from a place called the Coma Cluster, a dense collection of galaxies over 300 million light-years away. In the early 20th century, astronomers observed that the galaxies within the cluster were moving far too quickly. By visible mass alone, the cluster should have flown apart, but it did not. The only explanation was the presence of unseen mass, something providing the gravitational glue. Decades later, this mysterious force would be named dark matter, and it would redefine our understanding of what the universe is made of. Yet dark matter is not evenly distributed. In some galaxies, it dominates. In others, it appears to vanish. One of the most puzzling cases is a galaxy called NGC 1052-DF2. Observations suggest it contains little to no dark matter at all. Its stars move in ways consistent with the gravity of normal matter alone. For scientists, this is a mystery wrapped in contradiction. If dark matter is essential for galaxy formation, how did this one emerge without it? Or has something else tricked our instruments and assumptions? These anomalies do not disprove the existence of dark matter, but they remind us that our models are still incomplete. They force us to ask deeper questions. What is dark matter really made of? Is it a particle, a field, or something else entirely? Could it interact with itself or with regular matter in subtle, hidden ways? The more we learn, the more elusive it becomes. Like shadows cast by light we cannot see, dark matter remains one of the most profound mysteries in modern physics. We map its influence, but its nature slips through our fingers. In studying galaxies and dark matter, we are not merely cataloging structures. We are tracing the invisible bones of the cosmos. We are learning how matter gathers, how it clusters, and how complexity emerges from simplicity. Every spiral galaxy, every dwarf companion, every cluster is part of a much larger web, one spun from dark threads we cannot observe directly, but which guide the motion of everything we can. To understand galaxies is to follow those threads, and in doing so, we edge closer to understanding what the universe truly is, and what it hides. In the vast darkness between galaxies, there are stars so far away that their light has traveled across nearly the entire age of the universe to reach us. For most of human history, such stars were beyond our grasp, too distant, too faint, swallowed by the light of the galaxies they belong to. But now, with the power of gravitational lensing and the precision of the James Webb Space Telescope, we have begun to spot these ancient beacons. They are not just distant objects. They are solitary witnesses of a universe just awakening, and each one tells a story written in light older than Earth itself. The first of these discoveries came with a star named Icarus, found in the spring of 2018 using the Hubble Space Telescope. Its official name is LS1, but the name Icarus suits it, an echo from mythology, reaching toward the impossible. Icarus lived more than 9 billion light-years away, and it was only visible to us because a galaxy cluster in the foreground bent and magnified its light. It was the first time a single, normal star had ever been seen at such a distance. Before that, only entire galaxies could be resolved from so far away. But even Icarus would soon be surpassed. In early 2022, the James Webb Space Telescope identified a new record holder, a star named Earendel. Its light began its journey over 13 billion years ago, when the universe was less than 1 billion years old. That makes Earendel the farthest star ever observed. Through gravitational lensing, its light was magnified enough for Webb to isolate and study it. Scientists believe it may be a massive B-type star, bright, hot, and young. Yet what we see now is not the star as it is, but as it was long before Earth was formed. These stars are more than distant specks. They are keys to a forgotten time. By studying them, astronomers can better understand the conditions of the early universe, the composition of matter, the formation of the first heavy elements, and the life cycles of the first generations of stars. Some of these early stars may belong to the elusive population 3, the very first stars made entirely from hydrogen and helium, untouched by metals. No such star has yet been confirmed, but each new discovery brings us closer to that moment when the cosmos first lit itself from within. To see a star across 13 billion light-years is not just a technical achievement, it is a philosophical one. It reminds us how vast the universe truly is, and how much of its history remains hidden in darkness. These stars shine not just with light, but with memory. They are the loneliest beacons ever found, their photons stretched across time and space, whispering the secrets of a universe still in its infancy. And thanks to the instruments we have built, we can now hear them speak. In the endless expanse of the cosmos, there is a point of light so faint, so distant, that it defies ordinary comprehension. It is called HD1, a galaxy that may be the farthest object ever observed by humanity. Its light began traveling toward us over 13 billion years ago, from a time when the universe was less than 400 million years old. That means we are seeing HD1 not as it is now, but as it was when the first galaxies were just forming, when the cosmos was still in its infancy, clothed in darkness and beginning to shine. What makes HD1 remarkable is not just its distance, but its nature. It appears to be forming stars at an astonishing rate, perhaps hundreds of times faster than the Milky Way does today. It may be a starburst galaxy, one undergoing an intense and brief phase of creation. Or it may be something even more exotic, a host for one of the universe's earliest supermassive black holes, shining as a primitive quasar. Whatever the truth is, HD1 is not just a record breaker. It is a mystery that challenges our understanding of how galaxies assembled so quickly, so soon after the Big Bang. To detect a galaxy like HD1 is to peer across almost the entire observable history of the universe. Its redshift is so extreme that its light has been stretched into the deepest parts of the infrared spectrum. Without instruments like the James Webb Space Telescope and its unparalleled sensitivity, such a signal would be lost. But thanks to this technology, we now hold in our hands the light of a newborn galaxy, a fragile echo from the dawn of time. And in that light, we glimpse the seeds of everything we know: stars, planets, and the possibility of life itself. Beyond the orbit of Neptune lies a region cloaked in cold and silence, a vast, frozen frontier known as the Kuiper Belt. It is a ring of icy bodies, relics from the dawn of the solar system, orbiting the sun in darkness. These objects are ancient, untouched by the heat and violence of the inner solar system. They have remained there for billions of years, suspended in time, preserving the chemistry and chaos of our system's earliest days. To study the Kuiper Belt is to study the blueprint of how planets formed, and perhaps even how life began. The Kuiper Belt stretches from about 30 astronomical units to well beyond 50, forming a wide, donut-shaped halo of rock and ice. It contains dwarf planets like Pluto, Haumea, and Makemake, along with countless smaller bodies called Kuiper Belt objects. These objects are not merely debris. They are the leftover building blocks of the outer planets, primordial bricks that never came together to form something larger. Many contain water ice, methane, ammonia, and organic molecules, the same ingredients that may have helped seed the early Earth with the raw materials for life. For decades, the Kuiper Belt remained unseen. It was only theorized in the mid-20th century and confirmed by observation in the 1990s. But everything changed in 2015, when NASA's New Horizons spacecraft flew past Pluto and revealed it to be a world far more complex than anyone imagined. Its surface was sculpted by glaciers, mountains of water ice, and vast plains of frozen nitrogen. Beneath its crust may lie a subsurface ocean, and all of this existed in what we once thought was just a dead, frozen rock at the edge of the sun's reach. After Pluto, New Horizons continued deeper into the Kuiper Belt. On New Year's Day of 2019, it encountered a small, ancient object known as Arrokoth, a contact binary shaped like a snowman, untouched since the beginning of the solar system. Arrokoth is the most primitive object ever visited by a spacecraft. Its smooth, reddish surface hints at complex chemistry. Its gentle formation suggests that planetary building blocks may have come together slowly, not violently. In Arrokoth, we see not only the past, we see the method by which structure emerges from cosmic dust. The Kuiper Belt holds more than just icy bodies. It holds questions. Why do so many objects follow unusual, elongated orbits? Why is there a sudden drop in material beyond 55 astronomical units? These anomalies have led some scientists to propose the existence of a hidden world, Planet 9, a massive planet yet unseen, lurking in the darkness. If it exists, it would reshape our understanding of the solar system's formation and architecture. But whether real or not, the very search pushes the limits of what we can see and challenges the boundaries of our solar map. Even now, the Kuiper Belt remains largely unexplored. Of the estimated hundreds of thousands of objects it contains, only a few have been studied in detail. Many are no larger than cities, dim and cold, drifting through a twilight that never brightens. But hidden among them may be the molecular precursors of life, the same compounds that rained down on the early Earth in ancient impacts. In studying them, we might not only learn how planets grow, but how biology can arise from chemistry, how warmth can spring from ice. In the Kuiper Belt, we find echoes of origin. It is not merely the outer edge of our planetary system. It is a museum of frozen time, where the chaos and creativity of the early solar nebula remain intact. Each rock, each icy fragment, is a chapter in the long story of how order emerged from disorder. And though these bodies lie far from Earth, they are part of the same cosmic story that made us. By reaching toward them, by listening to their silence, we hear the distant whisper of our own beginning. In the late summer of the year 1977, two spacecraft rose from Earth on columns of fire. Their names were Voyager 1 and Voyager 2. They were built not to return, but to leave, to journey beyond the planets, beyond the sunlight, into the deep unknown. Each one carried a message, a golden disc engraved with the sounds and images of our world, laughter, music, greetings in many languages, and the heartbeat of a human being. They were not just machines, they were emissaries, silent messengers sent across the stars, carrying with them a trace of who we are. Voyager 2 began first, flying past Jupiter and Saturn, then doing what no spacecraft had ever done, visiting Uranus and Neptune. Its twin, Voyager 1, followed a faster path toward interstellar space, focusing on Jupiter and Saturn in greater detail. These encounters changed our understanding of the outer planets forever. We saw the swirling storm of the Great Red Spot, the icy rings of Saturn glowing like glass, the volcanoes of Io, and the frozen crust of Europa. The Voyagers turned distant dots into dynamic worlds, alive, strange, and stunning beyond imagination. After completing its planetary mission, Voyager 1 had one final task. At the urging of astronomer Carl Sagan, it turned its camera back toward Earth from a distance of over 6 billion kilometers. What it captured was a single point of light, smaller than a pixel, suspended in a sunbeam. This was the pale blue dot. In that image, everything we know, every war, every triumph, every love, every life, was contained in a single speck. A home both fragile and miraculous, floating in the dark. It was not just a photograph, it was a revelation. Carl Sagan would later reflect on the meaning of that image. That is here. That is home. That is us. He reminded us that Earth is a mote of dust in a vast cosmic arena. Our posturings, our imagined self-importance, are illusions against the scale of the universe. The pale blue dot calls for humility. It urges kindness. It teaches us that our only home must be cherished, not just for ourselves, but for the generations to come. Voyager showed us the planets, but more importantly, it helped us see ourselves, clearly, quietly, from afar. That backward glance was Voyager's farewell, a last look before disappearing into the void. And yet, that small act of turning back became one of humanity's most profound moments. It was as if the universe held up a mirror, and in it, we saw the wonder and fragility of our existence. In that fading light, the mission of Voyager took on a deeper purpose. It became more than exploration. It became memory, art, philosophy. A reminder that even as we reach for the stars, we must never forget the tiny blue world we call home. In the year 2012, Voyager 1 crossed a frontier that no human-made object had ever passed. It entered interstellar space, the the dark, silent region beyond the reach of our sun's wind. There was no signpost, no threshold. But instruments aboard the spacecraft recorded a shift. The solar particles thinned, and the surrounding plasma changed in frequency. Voyager had stepped outside the solar bubble and into the wider galaxy. It was no longer a planetary explorer. It had become an interstellar traveler, carrying the touch of Earth into the unknown. Six years later, Voyager 2 joined its sibling in crossing the heliopause, confirming the journey was no anomaly. Each spacecraft now sails through the interstellar medium, a vast sea of ancient atoms and ghostly magnetic fields. Though their instruments are aging, they continue to whisper home, sending faint signals across the void. These signals are more than data. They are lifelines, connecting us to the farthest expressions of human exploration. The Voyagers do not just move through space, they mark the edge of what humanity has touched. Both Voyagers carry something more than sensors and circuits. Fixed to each spacecraft is a golden record, a copper disc encased in gold, etched with the sights and sounds of Earth. It includes greetings in 55 languages, music from Bach to Blind Willie Johnson, the laughter of a child, the sound of a heartbeat. Etched upon it are mathematical symbols, star maps, and DNA sequences. It is a time capsule, a message in a bottle cast into a cosmic ocean. If ever found, it would speak not of our power, but of our longing to be known. Long after their instruments fall silent, the Voyagers will continue to drift. In 40,000 years, Voyager 1 may pass within sight of another star. In millions more, they may orbit in the gravity wells of distant suns or be lost to the dark between galaxies. But their journeys will outlast human cities, languages, even civilizations. They may be the last remnants of our species long after Earth is changed or gone. These spacecraft are not only scientific tools, they are monuments, built not of stone, but of motion and memory. There is something deeply poetic about the Voyagers. They are small, quiet, and alone, yet they carry the voice of an entire planet. In the silence of deep space, they represent our most audacious hope, that someone, somewhere, might hear us. And even if no one does, it was worth the effort. To send a message into the cosmos is an act of courage. It says, "We were here. We tried to understand. We reached as far as we could, and we left something behind, not just machines, but meaning." Voyager may be silent one day, but its legacy will endure. It taught us that the edge is not the end, that beyond every known horizon lies another question, another mystery waiting to be touched. And though its voice may fade, its echo will remain in every telescope we raise, in every spacecraft we build, and in every eye that looks up and dares to wonder. Voyager is not just traveling through space, it is traveling through time. And somewhere out there, beyond light and silence, it still carries our name. In the grand structure of the cosmos, most things drift with the flow of gravity, pulled gently by the invisible web of matter. Galaxies expand outward as space itself stretches. That much we understand. But in 2008, scientists detected something strange, something moving against the tide. Clusters of galaxies across billions of light years appeared to be heading in the same direction, at incredible speeds, toward a point far beyond the edge of the observable universe. This motion became known as dark flow, and it remains one of the most unsettling mysteries in cosmology. To understand dark flow, we must first understand how we measure motion on cosmic scales. Using the cosmic microwave background, the afterglow of the Big Bang, as a reference, astronomers can detect tiny shifts in temperature caused by galaxy clusters moving through space. What they found was a coherent pattern, massive structures moving at nearly 1,000 kilometers per second toward a region in the sky near the constellations Centaurus and Vela. This was not predicted by any standard model. No known gravitational source could account for such a large-scale motion. The implications are profound. If true, dark flow suggests that something beyond our cosmic horizon, outside the limits of what we can observe, is exerting a gravitational influence on our universe. It could be a massive structure, like a concentration of matter far larger than any supercluster. Or it could be something stranger, a relic from before the Big Bang, a fingerprint from a previous cycle of the cosmos, or even the gravitational pull of another universe. In each case, it challenges the notion that our observable universe is all there is. Not all scientists agree on dark flow. Some argue that the evidence is statistical noise, or that more precise instruments have failed to confirm it. Others believe the effect is real, but misunderstood. The Planck satellite, launched to measure the cosmic microwave background with higher accuracy, did not detect the same signal. But Planck's methods differ, and interpretations remain open. What is clear is that something peculiar is happening on the largest scales we can measure. Whether it is dark flow or something else, the cosmos is more dynamic than we once believed. What lies beyond our cosmic horizon may never be fully known. The observable universe is limited by the speed of light and the age of space itself. Beyond that edge, light has not yet had time to reach us. If massive structures exist there, their influence might be felt only through indirect effects, like the motion of galaxies we cannot explain. Dark flow reminds us of a haunting truth. We live in a bubble of visibility, surrounded by a greater reality we may never touch. But even a whisper from that beyond is enough to shift our understanding. Whether dark flow is a window into something beyond, or simply a misreading of data, it has already served its purpose. It has opened our minds to larger questions. What else lies outside the cosmic curtain? Are there other universes pulling at ours? Or is space itself larger, stranger, and more connected than we imagined? In searching for answers, we are once again humbled. The universe does not always reveal its truths clearly. Sometimes it offers only a shadow, moving in the dark, pointing to something greater than itself. What is the shape of the universe? It is a question that sounds simple, like something a child might ask while gazing at the stars. But hidden within that question is a doorway to the deepest layers of cosmology. Is the universe flat, stretching outward forever with no edge? Is it curved like a sphere, finite yet unbounded, looping back on itself? Or is it open, like a saddle, expanding endlessly into a higher dimensional space? According to current observations, space appears to be remarkably flat, balanced between expansion and collapse, with almost perfect precision. Yet, even if the universe is flat, that does not mean it is infinite. It could be finite, but vast beyond imagination, its curvature so slight that no instrument has yet revealed the bend. Or perhaps it is infinite in both space and time, a cosmic plane stretching forever in all directions, filled with galaxies beyond number, beyond reach. We do not know, and perhaps we may never know. The cosmic microwave background gives us only a limited window. The universe could curve beyond our horizon in ways we are not built to see. And so, we build better questions. The shape of the universe is not only about geometry, it is about destiny. A flat universe dominated by dark energy will expand forever, growing colder and darker with time. A closed universe might one day collapse, folding inward in a great reversal. An open universe may drift into emptiness, never to return. These possibilities are not just technical, they are existential. They force us to face the limits of knowledge, to confront the possibility that we are part of something whose boundaries we cannot trace, whose origin we cannot remember, and whose end we may not witness. And so we return to the question we began with: why do we look up? Perhaps it is because the universe reflects something within us. It is vast, mysterious, and ancient, just as we are curious, searching, and brief. In the patterns of galaxies, in the whisper of starlight, we see the echoes of something eternal. Not certainty, but wonder. Not answers, but possibilities. The shape of the universe may never be fully known, but in seeking it, we shape ourselves, our science, our art, our sense of meaning in a cosmos without center. The journey across the stars is not just one of distance, it is one of thought. From the faint glow of the first galaxies to the dark pull beyond the cosmic edge, we have traced a thread through time, woven with light and gravity, silence and motion. In the end, the universe may not need to be understood in full. It only needs to be seen, with clarity, with awe, and with the humility of knowing that we are part of it. A brief flicker, a voice in the dark, a question forever reaching for the stars. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.